Welcome to a video that will verify the formula for the equation of a tangent plane to a surface. Let's start by taking a look at a graph. Here we have a surface in gray and we have a tangent plane in yellow. The two vectors I want you to focus on are the red vector and the blue vector. The red vector is a normal vector to the surface and the blue vector is a tangent vector to the surface. As you can see, they are orthogonal to one another, and therefore that means their dot product would have to be 0. Also notice that the yellow plane would contain any tangent vector to the surface at this black point. One more thing I'd like you to notice. In purple, there's a space curve that falls on the surface. So if this space curve is on the surface, it would have to satisfy the equation of the surface. So with these ideas, let's go back and see if we can verify the equation for a tangent plane to a surface. So we'll start by letting z equals f of xy be written implicitly as big F of xyz equals 0. And we'll also let big F of xyz be differentiable at the point x sub 0, y sub 0, z sub 0. Next, we'll define a curve by a vectored valued function with components x of t, y of t, and z of t that contains the point x sub 0, y sub 0, z sub 0, and lies in the surface, defined by big F. So if this curve lies on the surface, that means if we substitute in x of t, y of t, and z of t into big F, it would have to satisfy the equation and therefore equal 0. And now we're going to differentiate this with respects to t. Now to differentiate the left side, we're going to have to apply the chain rule. This is going to be equal to the partial derivative of f with respects to x times dx dt plus the partial with respects to y times dy dt plus the partial of big F with respects to z times dz dt. And this would be equal to 0. Now let's take a close look at the left side of this equation. Here we have the partial derivatives of big F with respects to x, y, and z. And here we have dx dt, dy dt, and dz dt, which are the derivatives of each component of r of t, which means the gradient of big F dotted with r prime of t would be equal to 0. So it follows that the gradient and the tangent vector at our point x sub 0, y sub 0, z sub 0 are orthogonal to one another. It also follows that the tangent vector would be in the tangent plane. And contain the point x sub 0, y sub 0, z sub 0. So if we let x, y, z be any point on the tangent vector, we could rewrite the equation we had before where the gradient of f dotted with r prime of t would equal the gradient of f at the point x sub 0, y sub 0, z sub 0, dotted with the tangent vector with x component x minus x sub 0, y component y minus y sub 0, and the z component of z minus z sub 0 must equal 0. And so if we determine this dot product, we're going to have the partial of f with respects to x times x minus x sub 0 plus the partial of f with respects to y times y minus y sub 0 plus the partial with respects to z times z minus z sub 0 must equal 0, which is the equation of a tangent plane. So I hope this helps justify the equation that we used in the previous video to determine the equation of a tangent plane as we see here. Thank you for watching.